lastly, I'd like to state conclusions. Okay, so let us move to the first section. This shows about radix. We used only radix 2 in level 1. However, it is said that the radix 4 is most efficient generally. So 60 point or 64.50 can be performed with radix 4. On the other hand, 128.50 should be performed with mixed radix because 128 equals 4 times 2. So this figure shows CR4 diagram of 128.50 using mixed radix. In stage 1, we use radix 4. Similarly, in stage 2 and stage 3, we use radix 4. And finally, in stage 4 only, we use radix 2. Okay, let's move to next section. This figure shows pipeline architecture. And here, let me compare pipeline architecture and loop architecture. Pipeline architecture first. However, this is big. The select area becomes huge. On the other hand, loop architecture is compact. In addition, it is flexible if we perform large point with 50. Our circuit can perform 1024.50 and 4096.50 without changing fundamental circuit composition. Okay, this figure shows process flow of serial input and serial output to 50. Firstly, the input data is stored in the RAM, and then they are sent to the butterfly core and performed, calculated in it. And they are stored in the RAM again. So we can repeat this process as many as necessary. So lastly, we send to the data through output. So every point 50 can be performed by changing the number of loop times. So intermediate results are stored in the RAM. Okay, next slide, I will talk about butterfly core, and after that, I will talk about the architecture of this RAM. Okay, this figure shows permanent butterfly computation system. So I can perform both radix 4 and radix 2 in this circuit. In the case of radix 4, we need 3 steps. In first step, addition, 2 step, also addition. Finally, 3 steps. In 3 steps, it's multiplication. On the other hand, if we calculate radix 2, we use only these 2 addresses. Okay, let us move to next selling point. Okay, here I'd like to talk about memory configuration. Intermediate results between stages are stored in the RAM temporarily. It is necessary to input and output 4 data at the same time. However, the delay occurs if we attempt to read 4 data from one RAM. So we can use back architecture. Okay, however, I have a problem of back conflict. It is possible to read the 4 data at the same time. They are stored in a spread back. Please look at this figure. In this case, there is no back conflict. So we can read 4 data at the same time in one code. On the other hand, in this case, the delay occurs if the same data is stored in the same branch. So we need 2 clocks reading them. Okay, now let me compare 4-bank architecture and 5-bank architecture. This figure shows CR4 diagram or 16.50 using radix 4. And these colors represent bank number. For example, this green means bank 1, Okay, the rest one is for bank architecture. So if we calculate here, we have to read 4 data from these 4 banks. In this case, there is no conflict because they are stored in a separate bank. Similarly, if we calculate these 3 points, also there is no conflict. Okay. Next, state 2. If we calculate here, we have to read 4 data from these 4 banks. This case, but the bank conflict occurs because they are stored in all bank 0. All bank 0. Okay. On the other hand, this figure shows 5 bank memory architecture. In stage 1, similarly, there is no conflict. So in stage 2, if we calculate here, we have to read 4 data from these 4 banks. In this case, there is no conflict because they are stored in a separate bank. This is bank 0, bank 4, bank 3, and bank 2. This case, there is no conflict. So as a result, if we use 5 bank architecture, there is no conflict. Okay, let me show you four stages of our system. In order to control this private memory architecture, we need 2 selectors to control writing to this RAM and reading from this RAM. Okay, I'd like to talk about the control of writing and reading. This figure shows architecture of this RAM, of the RAM. So each bank has numbers of position. So I have to calculate the address of the range. First 3 bits means bank number. Also, this 5 bits means position number. Next, in order to calculate this address, we define these numbers 0, 1, 2, 3, 4, 5, 6, 7. So we call these numbers GID. It means global index. In next slide, in order to calculate this address, we use GID. Okay. Next slide. This figure shows a signal flow diagram of 16 point using radix form. These numbers are GID. Okay, let me explain how we calculate the address. Okay, if we calculate the address here, we use this equation. In this case, GID is 13, so 13 is divided by 5 equals 2 with a remainder of 3. Therefore, address is 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0. Okay, let us move to the next section. This chart shows synthesis record of our system and 50 exclusive of 1 second. Our system A can perform FFT up to 128 points. On the other hand, our system B can perform FFT up to 4096 points. Okay, next, I'd like to talk about the latency. If we perform FFT of 128 points. So in this case, our system is 231 clocks. However, so if we use radix to only not mixed radix and result using back dividing, in this case it means 899 clocks. So as a result, we succeed to reduce the latency 75%.
cũng không
Yeah,
phải
let
lên
us move to
89
next section.
899 nhiều quá.
I'd like to talk about implementation of a system. And we developed a real-time sound analysis system. So let me explain how to use it. First, we send the data from a smartphone to address road through line cable. Secondly, we perform NFT on address road. This is evaluation mode. Okay, thirdly, we send the results of NFT to a host PC through a USB cable. Finally, we display the spectrogram on this screen. Okay, here, let me show you a demonstration.
Lúc đang hỏi phần nào? Thế à? Thử quay hết cái này. Okay, mobile. Quay hết mobile.
Okay, firstly, we select 16.250. In this case, resolution of frequency is very low, so we can clearly recognize the change of frequency. This is peak frequency. Okay, next we change to 64.250. In this case, its resolution is better than 16.250. So we can recognize the change of peak frequency.
Hay là đây là cái tín hiệu truyền đi ra nhỉ? Không sao, đấy, đấy, cái nhô lên đấy là cái âm đấy.
Okay, finally, we choose 128.250.
Đúng rồi. Đây là tần số sao hết rồi? Sao phải nhớ? Nó màu đỏ này, đúng không?